All right. So hello, everyone. So it's a great pleasure. It is a great honor to speak at the conference celebrating the life and profound contribution of Rodney Baxter. And I would like, first of all, I would like to thank the organizer for this opportunity. My talk, I'm going to talk. My talk is related to the model, which was introduced by Baxter in 1970. In fact, the paper occurs in 1971. It's called Generalized Ferroelectric Model. Well, and first of all, to avoid any confusion, I should say that at that paper, Baxter studied the regime which characterize, well, the parameter Q, which is usually known as an anisotropy parameter, when this parameter is real. My focus of my talk would be the case when this parameter, anisotropy parameter, is unimodular number, and physics is very different. So actually, at least for me, it has always confused me. So this is a remark. So the idea for the model is come from the actually usual 6-vertex model. And the Baxter well, the solution of this model was done in by Lieb, the first solutions, but Baxter found own method of the solution, the method of commuting transfer matrix and all this business T and Q functions, which is known as in the book, in his book, it was called alternative method. And it's a very powerful approach, and among others, it allows one to generalize the 6-vertex model. So the 6-vertex model, it's well, it's very well known. I don't need to explain this. But the first step would be the parameterizations of the Boltzmann weights vertex. So I'm going to use zeta and q. Zeta is a spectral parameter, q anisotropy parameter, which I already mentioned. And then once the Boltzmann weights are organized in 4x4 matrix, they satisfy the Baxter equations, which is kind of central object in our conference and in whole mathematical physics now. Okay, so the next the idea, the Baxter idea, is that use the fact of that the central object is, of course, it's a transfer matrix, which is constructed from the local Boltzmann weight. And the important observations that the transfer matrix for different value of spectral parameter commute. So they form the commuting family of operators. The anisotropy parameters keep fixed. And in other words, so the problem reduced to diagonalizations of the transfer matrix. And then once we calculate the eigenvalues, you can calculate the partition functions, because the partition functions given by the trace of the power of the transfer matrix. So this is a basic pictures. In principle, next we can derive the Bethe-Ansatz equation and all this business, usual for integrability. But even from here, the immediate generalizations can be done for the model, and this was done in the paper I already mentioned. So the idea is, instead of the homogeneous transfer matrix, the transfer matrix built from the homogeneous Boltzmann weight, consider the consider the different Boltzmann weight. The difference is we keep the anisotropy parameter fixed, but change the value of spectral parameters shaded with the vertical lines, I denoted by eta 1, eta. Then the transfer, each individual matrix depend on the ratio of the spectral parameter which flow from associated with the vertical and horizontal lines. So the transfer matrix is given the formula, but now similar that was in the homogeneous case, but now it depends on extra parameter and homogeneity parameters eta 1, eta 2, eta n. But again, just using the Baxter equations, and this is advantage, it's a benefit for choosing such a parameterizations, parameterizing the weight using the spectral parameter and anisotropy parameter. But again, the transfer matrices form the commuting family of operators. Basically, then it's signed for integrability, and we can proceed further. And the same in the same direction as before, because we can now define the model where transfer matrix elementary block and partition functions is given by the for inhomogeneous model would be expressed again at the trace of the product of transfer matrices. And what's important, that's kind of generalizations. If you, well, once the ideas of the method was formulated, the generalization looks rather straightforward. But anyway, the model which we have depends on many parameters. So it's a multi-parametric, multi-parametric statistical systems. And it would be interesting to understand how the effect on physics of all these parameters. But first, I would like to mention that the model related for different other famous models, statistical mechanics like a Potts model. Well, it's known from as work from Baxter 73. That homogeneous six-vertex model can be mapped to the Potts model. Well, but inhomogeneous model, six-vertex model, also can be mapped to the Potts model, but with the different coupling along the horizontal and vertical directions. This is a result of the work of Baxter, Kelland, and Wood 75 works. Another applications, early applications of this model, it was a observation that the model can be used to provide the, in the certain setup, provide the regularizations of the massive quantum field theory, namely Sine-Gordon model. In this case, we need to consider the inhomogeneities should be taken to be real, and lambda and lambda minus 1, we have alternating chain of inhomogeneities, lambda and lambda minus 1 for lambda for odd and lambda minus odd for even sides. And the parameter lambda would related, in this case, the system is gapped. In principle, we can consider this model, but this model is not critical, but doing the certain limit, scaling proper scaling limit, we can generate the mass term we can generate the mass term in the Sine-Gordon actions. All right, but again, but I would more interest in the critical systems. The critical means this classical statistical model have an infinite correlation length, but it's more convenient to talk about not about the classical statistical model, but about the spin chains. Well, one can consider the spin chains with the Hamiltonian, which commute to the belongs to the commuting families of operators. And then the criticality can be studied. It's easy to study the criticality using just study the spectrum of the spin chain Hamiltonian. In particular, we can, in the case of critical system, we can extract the information about the conformal field theory underlying the critical behavior through the 1 over the n corrections. Well, the kind of archetypical example, it's a relation between the six-vertex model and XXZ spin chain. So the system is critical when a unimodular parameter, when the anisotropy parameter is unimodular number. And in this regime, the critical behavior described by the one compact boson with the compactification radius depend on anisotropy parameter. Gamma, co-gamma, the formula is rather well known. Okay, but what about the inhomogeneous six-vertex model? So in this case, it's turned out the model is critical to the necessary condition that it is, well, it's not proven, but it's expected that we still need to require that Q is unimodular. So again, it's given by the same formula like an usual six-vertex model. But inhomogeneity should satisfy a certain set of conditions because in general they're not critical. The model are not critical. All right, and so among the conditions, it seems rather natural to impose so-called Herside periodicity condition. It means that the patterns of inhomogeneity would periodically repeated with the period r. R is integers, which kept fixed. Then in the limit, when goes to infinity are fixed, we may expect the occurrence of the translation invariance in the continuous theory. Also, we can, since everything depends on the ratio of the parameters, so we can always impose some normalization conditions. So the number of parameters in transfer matrix would be n minus r minus 1 homogeneity parameters, and also together with the anisotropy parameter q. This is a peak. So in particular, the simplest situation, the case of the Stacker model, we already mentioned, when we have only two different values of homogeneities, so they alternated, right? And I already see that if once you choose the homogeneities to be real, to be real, then the system is actually develop the gap. It's not critical. The critical behavior occurs when homogeneities are unimodular as anisotropy parameter. So in other words, a critical system will characterized by two parameters alpha and gamma. Both of them can be chosen in the domain from 0 to pi, in the segment 0 to pi. So here is this case R equal 2, the case of the staggered models. Now it's relatively well studied. So in the phase diagram looks like this. So we have a triangle alpha, it's an homogeneity parameter, gamma is an isotropy parameter. We have this squared, and alpha equal to 0. We have a homogeneous model which characterized by the field theory, just a conformal field theory of free compactified bosons. So the behavior occurs in whole green domain. Then in this picture, the important line is so-called the line AB, which is a two symmetry line. In this case, then homogeneities eta 1 equal I, eta 2 equal minus I. So and the system possesses some additional global symmetries. And this line, especially in the domain in the segment AO, was studied, originated by the work, pioneering work of Jacobson and Salor, and then Eclipse Jacobson Salor. It was interesting, rather interesting critical behavior, rather interesting underlying conformal field theory, which is related, in particular, the spectrum and the model contains there's a spectrum conformal dimensions continuous, and it in principle and it can be described in terms of the nonlinear sigma model with the target space when the metric target space is so-called black hole metric, two-dimensional black hole metric, and so many interesting phenomena happened in this domain. And in fact, it was shown by Fram and Seal that in this black hole domain, in the blue domain, the parameter alpha and it's not relevant at all, and the same type, and nothing depend actually, nothing depend on these parameters. So in principle, once you study this, the universal behavior that doesn't depend on this parameter, and once you study the behavior system on the segment AO, then you actually it's done. You don't everything is more or less immediately translated to the whole triangle. And finally, we have another domain, I call it GAGM, which is a generalized affine Gaden model domain. For some reason, it's called this. The conformal field theory is more or less standard. In this case, the theory can be the underlying theory. It's a conformal field theory. It's built from the compact boson, like an XZ chain, but you need to add some two Majorana fermions, and that would be the conformal field theory. But and the conformal structure of the model doesn't depend on where you choose in whole triangle. The conformal structure is the same, but integrable structure is depend on parameter alpha, in the sense that even in continuous theory we have a set of commuting integral of motion which acts in conformal in continuous space, conformal Gilbert space, and the integral of motion depend on alpha, contrary to the case of the black hole domain. So that is a picture. And what we can, the important lesson we can learn from this picture, that in principle, to have an idea about the conformal critical behavior, it would be enough to focus on the some line with additional global symmetry, in this case Z2 symmetry. In the case of R side periodic model, the number of parameters is very large, but nevertheless, we still it makes sense to start with the situation when the model possesses additional global ZR symmetry, not Z2, because in that case, R equal to two-side periodical model. But now we have ZR symmetry once and homogeneity are primary are roots of unity and given by that formula. Okay, and again, so in these situations, we have only one parameter, gamma, which is an anisotropy parameter. But now, contrary to the homogeneous case, the domain, the segment from 0 to pi should be split on the equal size segments, pi over r. And we have a different type of critical behavior in each segment. You see, for r equal 2, you see this is for and on line AB, right? We have two segments, two domains, black hole domain, which is blue, and GAGM domain, which is red. And this is similar what we have here. Okay, and this type of behavior for arbitrary R, the critical behavior was studied in our work with Gleb Katausov in the case which is in the segment which is close to the boundary pi. In this case, the theory, the conformal field theory is built from R compact bosons. To be more precise, we should consider the R copy of the SU2 Kac-Moody algebra at level 1. In the deformation, it's make a certain deformation along the U1 subalgebra. All right, similar like in deformations, compactification radius for just a case XXZ spin chain. Then the most interesting domain is a blue one near the point gamma equals 0. In this case, this kind of it's similar to black hole domain. I believe that it's most interesting, and that a lot of interesting phenomena happen here. In particular, for even R, it's the field theory contains continuous component, conformal field theory continuous component, and also remarkably that each conformal primary state for in this field is conformal field theory is infinitely degenerate. So this is also quite unusual. But actually, the model, the regime I would like to discuss more. This was already discussed, and today I would like just to make some announcement of kind of new results concerning another regime, which is exactly in between, in the middle of the domain. But first, I would like to say how we studied this. And we use the Baxter, we use the Bethe-Ansatz equations, and then study the scaling limit of the beta roots, and from there we can extract the information about the field theory. So this is idea, and so this Bethe-Ansatz equation, which was written for Baxter for any regime, doesn't matter what. So in principle, this is a result of Baxter. But the solution, of course, depends on the value of Q. Okay, and so the domain I'm going to talk, it's occurs in the...
Oh, your microphone is.
Sorry.
Sorry.
Sorry?
Sergei's microphone.
It's
Yes,
so...
now it's good.
Okay, it's good?
Yeah, that's good.
Okay, can you hear me?
Yeah. Yes.
Okay, good. So this is this is about the this is appears in the case when R is odd. Then we have the following pictures, and we have a central domain, exactly, and which contain the point pi over 2, right? Pi over 2. I call this point pi over 2 free fermion point, because in this case, Q equal I, and if you take a look on the Bethe-Ansatz equations, the right hand side is can become simplified dramatically. So the equation is very simple. It's a set of independent algebraic equations, very simple algebraic equations. And so classification, in this case, we can classify the state for free fermion point, but classification remains the same once we slightly deviate from the free fermion points. So the situation similar that as a Landau Fermi liquid, when we can classify the interacting system using the classification for Fermi gas, non-interacting Fermi gas. So in this case, what we have here, we will have the field theory contains the R copy of Dirac fermions at free fermion points. Or currently, we can describe classify the state using the Kac-Moody algebra SUR Kac-Moody algebra at level 1, and also together with the compact boson. And the deformation from the point would correspond to the change of computation radius. So basically, the picture of the field theory is rather clear. And by the way, if you write explicitly the spin chains, the Hamiltonian spin chains for this case, so they're very similar to what the Professor Alcaraz presented in the previous lectures, right? Unfortunately, I will not keep all his talks, but it seems to me this point is very related to the model discussed by Francisco and maybe useful in this respect also. Okay, and so now how much time I have? Sorry.
You have 6 minutes.
Okay, good. Finally, I would like to say a few words about what happened with the scaling. Well, the scaling of the beta roots for in this regime. So first, the picture of the beta roots, the typical picture of beta roots is presented on these pictures. For the vacuum, right? And what's interesting, and when number of sites became very large, then the roots, which is on the edge of distributions, developed a certain scaling behavior. So in such a way that the following limit exists, right? So we can scale the roots in the vicinity of edge of distributions with a certain power and get the finite numbers. So this is a scaling, and this is very important information. It contains all information, the integrable structure of corresponding conformal field theory. So basically that's rather important. useful and important to study the Hilbert space and whatever. Okay, and for free fermions, such a scaling is easy performed. That is advantage of this point because algebraic equation is very simple. So doing the scale, we can immediately get the answer for these universal numbers occurs in the scaling limit of the beta roots. And one can easily observe that these roots related to the energy spectrum of harmonic oscillators, right? And given by this formula. And this is not accidental relations because it can be generalized for the interacting systems once we deviate from the free fermion points. The scaling of the vacuum beta roots still can be described in terms of differential equation, but now it's an anharmonic equation. The parameter of anharmonicity related to the parameter delta, which is deviation from the free fermion point. In fact, we can choose it would be, in many cases, it's more convenient to work in certain different coordinates and perform the exponential change of variables and write the equation such a way. And the advantage of this equation is that now we can write the equations which describe the scaling of the beta roots not only for the vacuum but any beta states, and this is given by such an equations. So this is a result of our recent work with Gleb Kutaus and Daria Shebetnik, who is a graduate student, my gradient student. This is an equation which contains some additional singularity, which is a apparent singularity in certain algebraic equation, which certain restrictions should be imposed on the position of singularity. So what I would like to just mention is that for R equal 1, the above ODE provides a different but equivalent descriptions of the quantum KdV integrable structure compared to the monster potentials. The potential was introduced in our work with Volodya Bazhan and Sasha Zamolodchikov a long time ago. So that is interesting, but the system looks even nice. For me, it's much nicer than its monster potential equations. But anyway, so now I'm probably should finish. So in my talk, I just briefly discussed the inhomogeneous six-vertex model and say a few words about the different type of critical behavior to regime. But the critical property of Baxter model are not fully understand. It still seems to me rather interesting questions from the physical point of view and formal mathematical point for theory differential equations and all this business with ODE KFT correspondence. Okay, thank you very much. Hello?
Thank you very much. Thank you very much. You have time for questions. Yeah. So I have a question. So we do have monster potential, which by definition shouldn't be very pleasant to look at, but your monster potential are better.
The equation looks better. The equation actually better and kind of more. You see the free fermion structure. We see remarkable features of this equation, of these potentials. By the way, if you take a look closely at these potentials, that delta equal to 0, the potential disappeared. The singular terms, additional term disappear, and we rest with only with the vacuum potential. Right? It's kind of strange, right? But remarkably, that performing the proper limit, doing the proper limit, doing the limit, you get a free Fermat point for all excited state. So that is a kind of strange situations. The potential looks for me it looks better in certain senses look better. That at least I can better understand the solutions and classifying it with the classifications. It's in the equations you can easily But in potential delta, if you set delta equal to 0, you end up with just vacuum potential. But equations, algebraic equations systems, right? At delta equal to 0 becomes it's rather meaningful, and this is exactly what what we have for free fermions, right? You see the solution expressed in this case equation trivialized, but anyway, so what I say that it's interesting that I don't understand. Principle, I understand how relate this potential with the monster potential, because it's of course it's kind of change of variables, but the systems a relation between the solution of this system and the solution of algebraic system for monster potential, it's absolutely not clear how to directly relate it.
Sergei, a question about a possible variation of your model. I mean, what happens in case you introduce open boundary conditions? I remember a paper by Fram and Kotosov and German, and I think they had systems with a non-compact spectrum, and that disappeared when the boundary condition was changed. What do you expect for your system?
Frankly, I don't know. Well, we focus mostly on we focus only on the quasi-periodic boundary conditions. For some reason, it's easy, but I don't expect that this need well, at least for the black hole case of the black hole domain, and in principle, more or less everything can be generalized. But of course, this part of the spectrum may disappear, but the equation model is the same. If you talk about the differential equation, but the technically it may be be not quite straightforward. At the moment I'm not ready to discuss this point for what happened in the boundary for this.
Okay. Let's thank the speaker again.